Walk into any modern hyperscale AI data center right now. You aren't just looking at rows of server racks, you are basically stepping into a loud, vibrating industrial furnace.
Yeah, that's exactly what it feels like.
Right, and we spend so much time discussing the software side of the AI boom, like the neural networks, the natural language processors, the generative art, that it's surprisingly easy to ignore the physical reality making those algorithms function.
Well, and that physical reality is running incredibly hot. It is totally starving for power.
Exactly. Just to contextualize the scale we're dealing with today, the top hyperscalers, companies like Meta, Google, Microsoft, and Amazon, they are ramping up their data center capital expenditures by 45% in 2025 alone.
Which is just a massive, massive jump.
It really is. And the lingering question hanging over the entire industry, and really for you, the listener, is how our physical grid and our cooling infrastructure will handle this unprecedented demand for energy.
It's basically the defining bottleneck of our current technological era. The industry is just colliding with the hard physical limits of traditional hardware.
So that brings us to our mission for this deep dive. We are looking at a relatively under-the-radar Swedish company called Sivers Semiconductors.
Right. They're doing some fascinating things.
They really are. They are quietly positioning themselves to solve this global data bottleneck, becoming a core enabler of a greener data economy. I was reading through their 2024 annual report alongside a stack of highly technical product specs and their latest April 2026 press releases.
And there's a lot of dense data in there.
Oh, absolutely. But what stands out is how they are attacking this problem at the microscopic level to yield macro-level energy savings.
As we explore their strategy, you have to keep two powerful multi-decade secular trends in mind.
What are those?
Well, everything Sivers is building sits at the intersection of AI acceleration and millimeter wave adoption. Yeah, this is fundamentally a story about the absolute physical constraints of moving data from point A to point B and how we have to completely rethink the physics of that transmission.
Okay, let's unpack this, starting with the inside of those data centers. To grasp the value of what Sivers is engineering, you first have to identify the bottleneck, right?
Right. And for over a century, the gold standard for electronics has just been copper wire.
But relying on electrical copper wires for modern AI workloads, it's like trying to force a fire hose of water through a standard plastic drinking straw.
That is a great way to picture it. The friction creates severe heat, it wastes a profound amount of energy, and it just slows the entire system down.
Why exactly does it slow down, though?
Well, it's the underlying physics of that friction. As AI training models scale up to require real-time inference, the volume of data traveling between processors, the CPUs and GPUs, becomes astronomical.
Right, we were talking terabytes upon terabytes in fractions of a second.
Exactly. And when you push data through copper interconnects at those extreme frequencies, electrical resistance kicks in. The signal degrades.
So you have to pump more power just to get it across.
Yeah, exactly. To compensate, you have to pump more electrical power through the wire just to get the signal to the other side.
Which creates more heat.
Right. That resistance generates heat, which forces you to consume even more power to run industrial cooling systems to prevent the servers from literally melting. It becomes a highly inefficient, self-defeating loop.
So the proposed solution here is to abandon electricity entirely for data transfer and transition to light.
Yes. Sivers is pioneering this shift from electrical I/O to optical I/O.
Based on their technical sheets, they specialize in high-precision distributed feedback, or DFB, laser arrays. And they utilize a proprietary indium phosphide processing platform they call NP100.
Right. They are quite literally replacing electrical signals with photons.
But wait, why use indium phosphide? Why not just use silicon, which the rest of the computing world runs on?
So silicon is phenomenal for conducting electricity and performing logic operations, but it's an indirect band gap material.
Meaning it doesn't emit light well.
Exactly. In simple terms, silicon is terrible at emitting light. If you pump current into silicon, it mostly just produces heat.
Which is exactly what we are trying to avoid in these data centers.
Right. Indium phosphide, on the other hand, is a direct band gap semiconductor. When you run an electrical current through it, it efficiently spits out photons.
And Sivers uses this material to create those DFB lasers. I read the distributed feedback part means there is a microscopic corrugated structure, kind of like tiny speed bumps, built directly into the laser cavity.
Yeah, those speed bumps force the laser to reflect and emit only one very pure specific wavelength of light.
Which is important for fiber optics, right?
Crucial, actually. You need it for sending clear signals over fiber optics without the light bleeding or degrading over distance.
The performance metrics tied to that pure signal are just staggering. In their collaboration with a partner called Ayar Labs, these lasers enable bidirectional speeds of 4 terabits per second.
And they manage that throughput while reducing power consumption by up to 90% compared to legacy electrical solutions.
90%? That's a massive drop.
It really is. By migrating these optical interconnects intimately close to every switch, GPU, and memory element, an architecture known as co-packaged optics, or CPO, the data travels as light.
Right, because photons do not suffer from the same frictional resistance as electrons. They don't generate that secondary heat.
Which cuts the power requirements drastically.
Okay, but let me push back a bit. Putting microscopic lasers next to vibrating, blistering hot GPUs sounds like a recipe for disaster.
Yeah, it definitely sounds fragile, yeah.
How does a highly sensitive optical component actually survive the grueling 247 demands of a hyperscale data center? I mean, you cannot afford a laser failing halfway through training a billion-dollar AI model.
Absolutely not. And that fragility has historically plagued optical computing. To counteract it, Sivers engineered a specialized ridge waveguide and dual-ridge architecture.
Wait, what does a ridge waveguide actually look like, and how does it prevent failure?
Think of a waveguide as a microscopic trench or a raised path carved directly into the semiconductor chip. Light naturally wants to spread out as it travels. Right.
Sure, like a flashlight beam widening out.
Exactly. The ridge acts like physical guardrails. It confines the photons, forcing them to stay focused and travel in a strict, tightly controlled path.
So this physical structure prevents the optical signal from wandering.
Yeah, which stabilizes the wavelength even when the surrounding environment fluctuates in temperature or vibrates violently.
The manufacturing process they use also seems to address the reliability issue. The specs mention an etched facet on-wafer testing process.
This is a huge deal. Traditional semiconductor manufacturing involves taking a circular wafer of chips and slicing it into tiny bars just to test if the lasers work.
And that physical cleaving process creates microscopic stress fractures, right? It introduces potential points of failure.
Exactly. Sivers bypasses that entirely. They chemically etch the mirrors of the laser, the facets, while the chips are still sitting on the intact wafer.
So they test the optics right there.
Yes.
They know the component is structurally sound before a saw ever touches it.
Right. And that changes the reliability mathematics completely. It yields an ultra-low FIT rate.
FIT stands for failure in time, right?
Yes. A FIT rate of 1 means you can expect 1 failure per 1 billion hours of operation. Sivers lasers boast a FIT rate of less than 1.
Wow, so you could run 1 billion of these components for an hour and statistically expect 0 failures.
Exactly. There are industrial-grade engines built for high-stress environments.
Which naturally pivots us to the commercial reality of this technology because, engineering a flawless low-FIT laser in a lab is vastly different from manufacturing millions of them to supply global hyperscalers.
Oh, definitely. Building a semiconductor fabrication plant costs billions of dollars.
Right. A company the size of Sivers cannot absorb that capital expenditure, so they utilize a fabless business model.
Exactly. They focus their capital exclusively on the intellectual property, the complex physics, and the architectural design.
And for the high-volume production.
They outsource to established blue-chip merchant foundries. Sivers partnered with W Semiconductors, which their CEO characterized as the TSMC equivalent for compound semiconductor foundry services.
Ah, okay. So WIN possesses the specialized, multi-billion-dollar facilities required to handle indium phosphide at scale.
Precisely.
Here's where it gets really interesting. We found an analyst's industry commentary referring to Sivers as the literal kingmaker for CPO.
That's a strong title to hold in this space.
It is. The analysis highlighted that early on, Sivers was supplying core technology to startups like Ayar Labs and celestial AI companies that now carry multi-billion-dollar valuations.
And today, Sivers is embedded within the heavy-duty ASIC ecosystem such as Marvell.
Right. The analyst noted that the broader market is just waking up to the fact that these major players are structurally designing their future data centers around Sivers light sources.
Embedding yourself into the foundational architecture of the data center is how you capture a deep moat. And they're looking at a serviceable market estimated at $2 billion.
Which is huge.
Just consider their strategic alignment in late 2025 with POET Technologies. They joined forces to capture a projected $1 billion submarket dedicated to external light source, or ELS, modules.
Right. So POET provides a highly integrated optical interposer platform, basically the optical motherboard, and Sivers provides the high-power DFB lasers.
Exactly. Together, they engineered a scalable, cost-optimized light engine aimed squarely at AI clusters, targeting full production readiness by late 2026.
I was looking at their April 2026 press release, which drops another major puzzle piece into place regarding their aggressive scaling. They announced a collaboration with Jabil, a titan in global manufacturing and supply chain management.
Yes, the Jabil partnership is key.
Together, they are producing a 1.6 terabit linear receive optical pluggable transceiver module, usually abbreviated as LRO.
And the standout metric in that release is that this LRO module operates at a 2.5 times lower energy footprint than standard modules.
But why is that energy drop so profound?
Well, to understand why, you have to look at what they actually removed from the device. A standard transceiver module typically houses a power-hungry digital signal processor, or DSP.
The DSP's job is to clean up and retime the signal before it hits the main switch, right?
Exactly. Linear receive optical technology strips that heavy DSP chip completely out of the pluggable module.
Oh, I see. So it takes the raw linear optical signal and passes it directly to the main switch chip to handle.
Yes. By removing that processing bottleneck at the plug, the power consumption plummets.
And the timing of that efficiency leap is critical. A light counting report cited in their materials projects that 800 gigabit and higher speed transceivers will dominate 80% of the market by 2030.
That's totaling roughly 225 million units shipped annually.
Wow. Having Jabil rely on Sivers components to manufacture these high-speed, low-power modules, I mean, that secures a massive footprint in that upcoming rollout.
It is a textbook execution of their fabled strategy. They engineer the highly differentiated photonic core, protect the intellectual property, and let heavyweights like Jabil and WO Semiconductors manage the global logistics and volume manufacturing.
So we have explored the subterranean world of the data center, where light is replacing copper to fix traffic jams on a motherboard.
Right.
But I want to shift our focus upward, because Sivers' wireless division is attempting to solve a remarkably similar data traffic jam in the sky.
Which ties into the second secular trend we mentioned earlier, millimeter wave and satellite communications.
The underlying physics problem mirrors the data center bottleneck, right? We're generating too much data, and the legacy highways just cannot accommodate it.
Exactly. In global telecommunications, the lower frequency spectrums, really anything under 6 gigahertz, are thoroughly congested.
So to find clean bandwidth and achieve lower latency, the satellite and telecom industries are migrating up into the millimeter wave frequencies,
Operating well above 10 gigahertz.
but transmitting at those higher frequencies introduces a whole new set of physical hurdles. I mean, you cannot treat a millimeter wave signal like a standard Wi-Fi router.
No, not at all.
A Wi-Fi router acts like a floodlight, blasting a signal indiscriminately in all directions. Sivers develops radio frequency beamformers, which act much more like a smart laser pointer.
That's a great analogy. They electronically steer a concentrated beam of data directly at a specific moving target, like a satellite orbiting the Earth.
Right.
What's fascinating here is how vital that electronic steering becomes when you factor in the proliferation of low orbit, or LEO, satellites.
Because LEO satellites operate much closer to the Earth's surface than legacy geostationary satellites.
Exactly. And because they are so close, they travel across the sky from horizon to horizon at breathtaking speeds relative to a receiver on the ground.
So a mechanical antenna physically cannot turn fast enough to maintain a connection.
Right. You need solid-state, rapid beam steering integrated circuits to track that satellite seamlessly.
And the demand for that tracking capability is compounding rapidly. The provided industry data forecasts the LEO satellite market surpassing $30 billion by 2030.
And every single one of those satellites requires ground terminals to function, specifically flat panel arrays.
The installation of those flat panels is projected to reach 3.2 million units by 2030.
Which is huge. And energy efficiency dictates the winners in the wireless sector, just as it does in photonics.
Because whether a flat panel array is mounted on a commercial airliner, a maritime vessel, or a remote off-grid installation, power is heavily restricted.
Exactly. Sivers engineered their RF beamformers to operate 3 to 5 times more efficiently than legacy components. Furthermore, they integrate a software technique called digital pre-distortion.
Wait, how does software solve a physical transmission problem?
So high-frequency amplifiers naturally warp or distort a signal when pushed to their maximum power limits. Digital pre-distortion anticipates how the physical hardware and the atmosphere will warp that signal.
Ah, I see.
Right before the data is transmitted, the software intentionally distorts the signal in the exact opposite direction.
Oh, that's clever. So as the signal travels and naturally degrades, it essentially bends back into a perfect, clean shape by the time it reaches the receiver.
Exactly. This allows the amplifier to run highly efficiently without needing to brute force a clean signal through pure electrical power,
It can reduce power consumption during transmission by up to an additional 50%.
which is massive for those mobile applications.
We can see that efficiency driving substantial commercial traction, too. Their recent financials detail a landmark digitizer development contract with Intelsat, a prominent fixture in global satellite infrastructure.
Right. Intelsat is integrating Sivers technology across their terminals, aiming for deployment starting in 2026.
And that traction is not limited to commercial broadband. The physics of targeted, high-frequency wave transmission appeal heavily to the defense sector.
Making this a highly lucrative dual-use technology.
Right, we see that dual-use validation in their government funding. Sivers recently secured 122 million Swedish krona, which is roughly 11.6 million US dollars, through 2 US CBS Act awards.
The first award accelerates their 5G and 6G array designs.
And the second focuses specifically on developing full duplex arrays for advanced electronic warfare applications, collaborating with defense primes like BAE Systems and Raytheon.
It really speaks to the foundational nature of their engineering.
Right, whether steering a broadband connection to a commercial aircraft or directing a secure tactical data link for a defense system, the requirement for reliable, energy-conscious, high-frequency beamforming remains identical.
The symmetry between their two divisions is striking.
It really is. I mean, in the data center, they are building guardrails for photons to travel efficiently across microscopic silicon. Up in the atmosphere, they are predicting atmospheric distortion to shoot radio waves at orbiting satellites.
In both environments, they serve as the crucial, power-saving traffic controllers of the digital world.
They are attacking the physical friction of data transfer on two separate fronts, yielding substantial power reductions in both.
Yeah.
So what does this all mean for you, the listener? Whether you are analyzing markets, following the AI boom, or just striving to comprehend the physical infrastructure of the internet, the lesson is that software eventually bows to hardware.
Exactly. You can write the most elegant AI algorithm conceived by human minds, but if the server's thermal throttle or the regional power grid cannot sustain the load, the algorithm stops.
The financial trajectory outlined in their historic reports illustrates a company transitioning from deep research and development into a phase of commercial execution.
Right, looking at those numbers, Sivers closed 2024 with record sales of 244 million Swedish krona.
And perhaps more telling, they achieved a 21% jump in adjusted EBITDA and a 32% increase in operational cash flow.
They're positioning themselves ahead of substantial macroeconomic tailwinds. Beyond the US CQPS, early 2025 saw the announcement of the European Commission's Euro 200 billion Invest AI initiative.
As one of the few European suppliers possessing this depth of advanced photonics expertise, they are openly targeting a major volume ramp in 2027 to meet government and hyperscaler demands.
If we connect this to the bigger picture, the limiting factor for human connectivity and artificial intelligence is no longer human ambition or coding capability.
Right.
The ultimate boundary is energy efficiency. Sivers is demonstrating that the only sustainable path forward for the data economy is to stop fighting the physical resistance of copper wire and omnidirectional broadcasting and start manipulating light and targeted waves.
Which leaves us with a provocative final thought to consider. We spend countless hours debating whether artificial intelligence will outpace human comprehension or if the software will become too advanced to control. But what if the ultimate ceiling on AI isn't an intelligence cap at all, but the physical limits of our universe?
That's a crazy thought.
Right. If companies like Sivers are already forced to replace electricity with light just to keep today's servers from melting, how long until the traditional silicon computer chip goes entirely extinct? Replaced by systems that compute entirely through optical physics. What happens to the pace of innovation when our machines literally learn to think at the speed of light?